Question 14 invites us to look at bond energies as a concept. So we are using these bond energies to figure out the overall energy change of a reaction. And it's the reaction between hydrogen and chlorine gases to produce hydrogen chloride. So here's what we need to do. We need to consider exactly what is happening in a chemical reaction. And to do that, I am going to draw an energy profile diagram just to help me out. So we've got energy on the y-axis and we've got progress of reaction on the x-axis. So let's imagine that we are here at the start of our reaction. We've got our molecule of H2 and our molecule of Cl2. Now, the first thing that you need to happen for a chemical reaction is that the bonds that are already existing between those atoms, they need to break. And in order to break those bonds, you need to put a lot of energy in order to break them. So breaking bonds is an endothermic process because you're putting that energy in, transferring it from the thermal store surrounding to the chemical store to break those bonds. Okay, that's what we're doing in an endothermic process. Now, we need to look at these bond energy values because that's the numerical data that kind of supports this. Now, what this value is saying is that if you have 1 mole of HH bonds, it will take 436 kilojoules of energy to break all of those bonds. That's what it's telling us. So we need to consider then this reaction. So we've got hydrogen plus chlorine forming 2 lots of HCl, and I'm going to draw both of those HCl molecules out like this, and you'll see why in a second. So first of all, I'm interested in the reactants. So I've got a chemical bond between hydrogen and hydrogen that I want to break. So I need to put in 436 joules, or kilojoules, sorry, I should say, per mole of energy. I've also got a bond between chlorine and chlorine, which I need to break. So that, we look at the value, is plus 242. So if I add these two values together, this will give me an answer of 678. And that is the amount of energy I have to put in to break all the bonds in the reactants. Now I'm going to show this on this diagram because I'm putting this energy in, so it's an arrow going up. I'm going to put plus 678 just there. And now we've got all of our atoms. They're not bonded together, but we're going to form some new bonds. And when new bonds form, that energy is released to the surroundings. So it's going from those chemical stores to the thermal store of the surroundings. Now, because it's going to the thermal store of the surroundings, because it's being dissipated, that energy, it's being released, what it means is that the energy change in the reaction is negative. It's going down. Okay, so energy is being given out to form these bonds. So that means it's an exothermic process. So we're going to find out how much of that energy is being given out. So this is why I draw out these two HCl molecules here, okay, because there is a 2 balancing it in the equation. I draw them out because I always like to cross off the number of bonds I'm breaking, just so I don't ever forget them. So in our products, we are forming 2 HCl bonds. So we're doing 2 lots of 431, and that gives me an answer of 862. Now, in this case, because that energy is being released, because the bonds aren't being broken, they're being formed, we can show it going down, okay, to our products here, which is our 2 lots of HCl. But I'm interested in the total energy change of this reaction, going from the reactants to the products. And we can see from my diagram, based on the sizes of the arrows I've drawn, that it's going down. It's going to be a negative value, because what I've done is I've put 678 joules of energy in to break the bonds, and then 862 joules of energy are coming out when the new bonds are being formed. So if you do that, 678 minus 862, you get an answer of minus 184 kilojoules per mole. So the trick to this is finding the total bond energy of your reactant bonds, that gets you a mark. Finding the total bond energy of your product bonds, that gets you a second mark. Then you need to do the reactants take away the products So the bond energies, all of the bond energies of the reactants, take away all of the bond energies of your products to give you the third mark, and then your final mark is for getting the final answer, which in this case, as I've said, is minus 184. Now we'll look at another example, which is a little bit more complicated because there's a few more bonds. So this time we're looking at the complete combustion of propane. So our reactants, I'm not going to draw the energy profile diagram this time, but our reactants, let's look at the bonds. We've got our propane drawn out over here on the left, C3H8. So let's count the CH bonds first. We've got 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 CH bonds. So I'm going to do 8 lots of whatever the value for carbon-hydrogen bonds are. Then I've got 1, 2 carbon-carbon bonds. So I need to include those. I've also got 5 molecules of oxygen. So once again, I'm going to draw all of these out to make sure I don't miss out any bonds. So 1, 2, 3, 4, 5. Yep, screw the 5 out to say that I've done that. And I'm going to count how many double bonds I've got between the oxygens. So I've got 1, 2, 3, 4, 5. So I've got 5 lots of the oxygen-oxygen double bond. And that's all of my reactants. So let's do the maths. We've got 8 lots of the carbon-hydrogen bond, which is 412. We've got 2 lots of the carbon-carbon bond, which is 348. We've got that from the table over here. And we've got 5 lots of the oxygen-oxygen double bond, which is 498. And if we do the maths there, we add all of those numbers together, we get plus 6482. If you get that, you get 1 mark. Now we move on to the products. So we see we've got 3 molecules of carbon dioxide. So I'm going to draw another 2 in there just so I don't miss any bonds out. So there's 1, and there's 2, and then the third one is the one that's already there. So scribble out the 3. So how many carbon-oxygen double bonds do I have? Well, I've got 1 here. I've got 1 here. 3, 4, 5, 6. So I've got 6 lots of the carbon-oxygen double bond. Remember, bonds can be the same going one way as the other. So C double bond O is the same as O double bond C because these things are three-dimensional. They can be rotated in space. So we've got 6 lots of the carbon-oxygen double bond. Now let's look at water. We've got 4 molecules of water. So again, I'm going to draw out another 3 just so I've got a total of 4 on there so I can see all of my bonds just to make it easier for me to keep track of what I've done already. So how many OH bonds do we have? Well, we've got 1 there, 2, 3, 4, and these are all OH bonds as well, just the other way around. 5, 6, 7, 8. So I'm going to add that to 8 lots of the OH bond. Now, if I do that calculation, we end up with 6 lots of the carbon-oxygen double bond, which is 743. We do 8 lots of the OH single bond, which is 463. And if you evaluate that, you get an answer of 8,162. And that will get you a second mark. The next step is to remember what way we do it. We do reactants minus products because remember we've got to put the energy in to break the bond, so that's why the reactant is positive and the energy is being released when the new bonds are formed, so that's why that one is negative. So it's 6482. We're taking away 8162. You'll get a mark if you've done that, and then finally your final answer will be minus 1,680 kilojoules per mole, because the units of the final answer will be the same as the units for all of your bond energies. Now you might be asked whether this reaction is exothermic or endothermic. Remember, if your energy change is negative, that means that this is an exothermic reaction, and if you get an overall positive energy change, it will be an endothermic reaction.